sometimes you will receive the critical lateral extension. I just simply write critical extension. So in my notes, I write the vacuum case. Here, just simply search out solution. Because he found two solutions. One is vacuum case, which is black hole solution. You also found one solution actually with constant energy density. So actually, this normally we consider internal solution. So now this actually we're just in actual vacuum case. So we have actually ds squared is equal f r dt squared minus dr squared f r minus r squared d squared. This is actually the case. Actually, we'll see. The idea is very simple. So we already use Einstein. In one time, we use advanced. Sorry, this actually. Then we also use. Time. So actually, now we want to combine. Instead of using VR, we just actually let's call I use another symbol W. We just use V and W. Then each symbol put them together. Remember we use one, at the one symbol to get a black hole, right? We use retarded time, we get white hole. Now I simply give up of using R. I use both. Advanced time and retarded time. Then you can see mathematically alone to put a white hole, black hole together. Right? So this is actually the main idea. So we already know this actually we introduce the dr star, the star coordinates. Right? So this actually F actually R, you can see this is D T plus dr star multiplied D T minus dr star minus R squared D squared. Right? I simply turn, this is my weight, this is my dot. I use this. Okay? So if I do something like this, so I have this one. In terms of this, but you can see now I have actually GVW equal 1 minus 2 MR G theta equal minus R squared G phi equal minus R squared and squared. Then GVW actually equal 1 over 1 minus 2 and R G theta minus 1 R minus R Now this guy is okay, right? This is 0. When r equal to and find that the problem here I still have single r. The coordinate is still single, right? The coordinate is still singular, that's fine. So we are going to like redefine this guy. You can see if I do the following. We say we introduce W equal V bar, V or inversely W bar equal W bar W. We have actually ds squared equal f dv bar dw dw bar multiplied dv bar dw bar. Right? So this equals r minus 2 and r multiplied dv bar dw bar. Correct? Now, by writing, you can see there's some hint here. What's happening if I properly choosing the relations, I can, if I have something like dv bar dw bar, give me something minus f hat r. F hat r is 1 r equal to infinite. That's exactly cancel this thing, right? Right? Everything is done. Okay? So this is so simple. Right? So now I just look around what's my V and W to actually make up one factor 1 over r minus 2. If I do this factor help me to cancel this one, then I have f hat r over r when r equal to everything. Fine. Right? You can do all these works. So this is exactly the ideas. Right? So you will see, even for the general case, we'll do something similar. So now, in order to see this point, we want to come back to this guy. So remember, r star equal r plus 2 log r minus 2 m, right? This is exactly what we need. Right? So if I have e to alpha r star, we get something. Right? This way. Okay? So this actually we have this one. You can see now, this is giving me some hint here. Right? So if we have this equation, now let's call this equation, I forget this number. Can we put a 15? We have this one. Now you see here, this equation in region 1 and in region 2, I can simply combine all the things to find this guy. Correct? So the idea is we have actually this V tail, the double tail in region 1, region 2. Actually, this I intensely draw this actually 45 degrees because it's T plus R, T minus R, right? So now, normally, we like to actually consider like T coordinates and X prime. I just simply use this T prime equal V tail plus double tail X prime because it's exactly 45 degrees. Now you can prove this is exactly 45. Not from different from T bar and R. So if I do this actually, this equation is true, then we find just apply this expression to here, I get then this one to here, I get a T prime and X prime in region 1. So I'm going to write here. This will be T prime equal R minus 2 and square root e to R equal 4 and hyperbolic sine T over 4n and X prime equal R minus 2 and square root cosine hyperbolic T over 4. So this is actually region 1. This is a corresponding from, you can see, TR to the T prime, X prime. Now later I'm going to show where this really, you can visually see this is sort of the, both of them are possible, right? Both of them are possible here. But you will see this, there are some constraints. Okay, so this actually in region 1. What about this east side level? This actually corresponds. So I'm going to actually plug in this one here, then here, then to get the solution in this region, right? So this actually will be lecture 6. So I'm glad we just catch up on half of this one, because otherwise we cannot finish this one. So I'm going to work out the details. You will see, because this part in formula science, you have like extension. So what's the map between the PR plane? The idea is here it was this is a flat channel coordinates. We have actually region 1, this is 2, and this is region 2. Because we have level here. Now, what's the relation here? We have actually this is a V pure W pure. Because this is 45, this is no coordinates are used 45. So later actually we will introduce this actually X. X prime, this is called T prime. Okay? So our idea is how we can, what's the map? You see here, we can consider V and W function of T and R. And this actually, remember V equals T plus R star, and W equals T minus R star, and R star equals R plus 2 and which actually is good in two ways. So our idea is actually to see what's the mapping between this actually T R plane to the actually weight field temperature. Then we identify, for example, this actually let's call inside the black hole region is outside. Then how mapped here. You will see this actually is a region 1, this actually is region 2. Here actually is one extended region to go prime this actually. This you will see this to the E prime square minus X prime square. Then T prime square minus X prime square. This is where equal 2m minus R E R 2n. These are all the greater than 0 for R less than 2n or equal. Right? So which means now I'm actually in this range. Correct? So this is enough. This is range. Because my T prime is a positive. Right? Meaningless. Keep our plane. So in this plane, actually, you can see now I have a, let's see, this is R, T bar. This is 0. R coordinates is the same. This actually is 2m, right? So this is what we call this range is 1, and this is 2. This is actually 1. To give it a name. So now in this case, you can say, okay, this guy is for the minus sign. For the minus sign, if I take a minus sign, I simply equal T bar equal minus R plus C0, right? C0 is constant. So if C0 equals 0, my T bar equal minus R, right? What's that means actually? This is a line C0 equal 0, correct? This is the yin grid. What's happening if I have this actually, if it's C0 negative, C0 negative, you can see, let's see, T bar equal minus R minus 2, right? This is actually negative case. So, or I can write a T bar plus R equal minus 2. My R equals 0, T bar equal minus 2. So this is minus 2 here. This is R equals 0. This actually, so this is C0 negative. Correct? What about C0 positive? You can just simply, this is C0 positive. Sorry, my drawing is always very bad. But this actually, clear is a yin grid line, right? This tells us what? You see, the line simply passes through R equal to m, get inside the black hole, right? So now we want to see what's happening with plus sign. Plus sign actually, I have a plus sign, this is actually the case. Let's use this. First, consider inside the black hole. Inside the black hole, let's write here, T bar equal R plus 4m log R minus 2 m plus C0. So if we consider, let's see, firstly inside the black hole, now let's consider R equals 0 case. R equals 0 log of 2m, finite. This equals 0, then we get actually, you can see, and T bar and R equals 0 equal actually 4m log 2m, right? Plus C0. Now, if my C0 larger than this actually positive, I have actually something like here, right? This is a case totally, this T bar is equal to positive. If it's 0, this is exactly equal to 1. This is here, right? So what about if one R go to 2m? R go to 2m, this is 2m. This is go to negative infinity, right? So I should get something like this. Correct? And if, like what I said, this two term is positive, I should get something like this. What I get? Or negative, I get something. Correct? So this actually, you can see. Why this is important? Remember, this actually the light travel. If any particle traveling less than the speed of light will be inside the light component. We learned this in special relativity. Now then you can see, okay, I have this point, right? So this one light come for this point, then all the particles passing my point, let's say P, will go towards to the singularity. Since this line will hit here, this one here, this guy has to be more or less hit at some point in between this, cannot go out. What's the physics? Physics said, okay, if let's say a human being or any kind particle with a mass, once they get in, there's no way for this particle stay there, always move to singularity, finally hit the point. Right? This is important. One day actually, I attend a conference, so scholars, it was a very famous scholars. He said, well, I found some actually particular behavior. I found a particle can stay stationary inside the black hole. So I tell him, no, it's impossible. I said, no, I just found it. I said, no, you just should actually bad current. Okay, this is simply draw the Pan's diagram. You do not need to draw Pan's diagram. They use add the fingers and current, so you know what's happening, right? There's no way to stay here. So always believe, because this is the light come. Correct? So what about here? Okay, I have this acre the east side, right? Any question about this?
This is the orange less than 20.
Yeah, this acre is y consider positive, y r less than 2m, right? We're going to consider what's happening when r greater than 2m. Let's see, if r greater than 2m, first, when r goes to infinity. R goes to infinity, so this guy goes to infinity, t prime, right? Which means I have something like this. This means t goes to infinity, r goes to infinity, right? So when r goes to m, again, this guy's log almost 0, minus infinity. This is always finite. 2m is finite. So I have something like this. Correct? So this should be asymptotically near the point. So I have another one comes. Correct? This actually should be the time direction always go up. This. You see here, this is a light come, right? So once you are outside, this is like another cube. This actually, this is a time-like geodesics. And at this point, this could touch outside, this can come out, right? So that's this actually, as long as this actually one timeline particles inside of outside of black hole, there are possibilities for this guy to skip different. But here, once you get in, there's no way to get out. So that's exactly the definition of a one-way membrane, right? Remember, black hole only get in, cannot come out. So that's exactly the definition of a black hole, right? So this actually, you see this line, you can prove this also light. Only light can stay on the R equal 2m, go here, then this is the point. Once you hit it here, you have no choice to get back. The only thing you have to get move inside the black hole. Okay? So this gives us clear picture. If something hit the R equals 2m, unless this particle has zero mass, rest mass, like light, the light can actually stay on R equals 2m, but all the particles has to get in. There's no way to turn back. So if I am outside of black hole, there is a chance for me to get it back, right? Because the light comes open to outside. Okay? Any question on this part? Okay, since this is actually very easy to understand, right? So, okay, I didn't finger snap on this actual black hole. Why we, until 1960, we call this a black hole? Because once we consider another part, this actually, the geodesics, we use, you see, T bar under R. I always introduce T stars. And what happened with the T stars? Then you will find T stars totally different, opposite. I have something only comes out, not get in. So what's that? If it's a black hole, everything get in, then you have something opposite of black hole. Coming out from region 2. So how you can understand this, right? So let's first consider T star on the R plane. Then we get some contradiction interpretations. Then finally, to the result this contradiction, we have to use Korsakoff-Zakhar's coordinates. There actually you can see, oh, this is cover only part of the whole space. And when we consider T star and R plane, that only cover another part of Korsakoff-Zakhar's full space. Then we understand, okay, this actually is solve this contradiction in the Korsakoff-Zakhar's coordinates. But we solve the contradiction. So far, I think we're still struggling to understand this. What's happening in university? We have white hole, black hole. We have 4 regions, 2 asymptotic regions. One is inside a white hole, another inside a black hole. So we believe white hole is not actually stable. So what's happening? I think we're still, honestly, we do not understand this here. We're still struggling. How in our universe exists this kind of things? We have white hole connected to black hole. Some people think the white hole is actually ejecting, then the things actually come out or focus each other because Einstein's theory is not linear, then form a black hole. But can you build this actually, build some model, show people this case? Right? So this actually is an open question. So before we get to that, so any question about this part? Okay. So now we want to see what's happening if we use T star and so we have actually T star. T star we define like T minus 2m log R minus 2m. This is our T star. But this actually the coordinates we know around the geodesic t equal plus minus r plus 2 and log r minus 2 and plus c0, then you have minus 2 log r minus 2, right? So then you can see now, if we choose plus sign, this actually plus, this guy cancel with this one, right? So I have a r plus c0. So, but if I consider minus sign, this is minus r. Here minus 2m log minus 2m, I get like minus 4. No, r minus 2. Plus 0. So this actually, so we have actually two solutions. This actually normally we call English. This really depends, you see here? Which region we are talking about, right? So this is always English. This actually can be English. Now we want to see what's happening actually. Instead of using T bar, we want to see what's happening in the actually T star. I'm going to erase this again to consider the planes. So we have actually here R T star 0 to M, right? So now let's first consider the plus sign, because the plus sign is easy. So this actually T star equal R plus C0, right? Now if I take C0 equals 0, this will be this line, right? The passing because the T star equals R. Yeah. So now if this actually C0 equals 0, what's happening if C0 negative? I have something like this. This actually is C0 negative. Right? So what about positive case? Positive case, just go back. C0 positive. So this actually, you can see now, time is on this direction, right? This is ultimately. This means, in this case, the line actually comes from the singularity, then go to infinity. So this is exactly contradiction to the black hole, right? Since comes from. What about another part?
So why does this come out?
Sorry?
Why does this come out? Can you explain this?
Yeah, this is because remember T star will consider always green, right? So this actually, for example, when T equal, there's a minus 10, the particle is heat singularity. When T actually, T star equal 10, minus 5 here. So plus 5 here. So this is always the optical, right? But this is straight line. This actually, this photon does not feel anything, just simply passes to end. Correct? This actually no geodesic, right? Yeah, good. Any other question? So now if we consider minus sign, you can see T star equal minus R minus 4 and log R minus 2 and plus C0. Again, we consider both M, let's say first M R less than 2M. R less than 2M, you can say when R equals 0, this is a particular you want to consider. This equals 0, this is minus 4M. This will be minus 4M log 2M finite plus C. So this is again depend on constancy. This can be here, right? Can be here, can be here, can be here. Can be in this vector finance volume. Depending on C, I think this is my point, right? Okay. What about when R equal to M? R equal to log of 0, again minus infinity. This guy is to M finite. So what I have is the following. You see, I have this one, go to minus infinity, minus infinity, minus infinity, minus infinity. Right? So this will go like this. Or I have something like this here, right? Again, you can see here, it's close, right? So I can have something, let's see, this actually, if I consider this is my last count, I have something. This P is always go outside. Finally, they will come out. Because now you can see this is the light count and towards to infinity. It's open. No, it's not closed. You see, even I have actually particles, let's see, from here this go to infinity, right? So this is actually the inside R. What about when R outside? R outside, you can see when R go to infinity, this guy is go to minus infinity, right? So I have something sort of comes minus infinity here. Let's see. But when R go to N, this is a minus infinity, positive infinity. So what I have something like that. Right? See, then you can see here, for example, if this point I consider, then this actually is the key point. Particle will go to infinity, right? So this is totally opposite to what we considered before. Here this tells us, even you are inside the twin, this particle can easily go to infinity. There's no problem. Right? So how do I understand this? So that's actually the main paradox. You see, if you use T star and T bar, if I use T bar, I can easily get out this black hole. So normally we think of solar shadow source as a black hole. But solar shadow source is also white hole. Right? See, you think of white hole. Everything just yeah. Okay, so the opposite of black, so white. So this seems to only come out, nothing actually can get in. It just actually comes from this. Remember this is single arc. That will be disaster to Einstein survey. Because if things come keeping pumps out from singularity, then our universe very soon will be closed. We have so much matter in our universe. The whole universe will collapse. Right? It's an attractive force. So now, this is the main point. How do I understand this? We know how to do actually a Kruskal diagram, or a Kruskal coordinates. Mathematically, I think we understand it very well. But only physically, we do not understand this quite well. What's this mean? Does this actually really exist in our universe? Or part of the diagram makes sense? Normally we believe only part. If you consider collapse, I do not have this part, something. But this is true. Like yesterday what I said, information get lost. This is why the information comes out. Right? How do I understand this? So the answer is not so sure. Right? So this is actually the point we have here. Any question about this part? So I think I just directly went to the adding finger synchronicity using advanced time V or retarded time V. That is called adding the finger synchronicity. You can write the metric in terms of T star and R. Then in my notes I'll have this one. Then the current you will find I have TT component, TR component, RR component. But you can find also even in that one, my metric, I measure the inverse of metric, still no signal. So that's fine. This coordinates in terms of T star are also called finger sign, adding the finger sign coordinates. But the normal one we say adding the finger coordinates, adding the finger sign coordinates, we always refer to the U R coordinate or V R coordinate, not the T star and T bar coordinates. Any question about this? I have a quiz. This picture correct?
No.
No.
R less than 2m.
Sorry?
For R less than part 2m, that's wrong.
R negative 2m? Okay. So why not correct?
Because minus, it should be minus log 0. So plus infinity. For R near to 2m, T star should be infinity, positive infinity.
But this is my T star, right? This is my definition. This definition actually is okay. I didn't introduce this one. I didn't plot this in the T star and R plane, right? Think about this. If this type, where is the, I'm going to write it down. The metric in terms of T star, R star, then you will see immediately what's happening. So let's consider ds squared equal so 1 minus 2mr d t bar squared minus 4mr d t bar dr minus 1 plus 2mr dr squared minus r squared d omega squared. This is actually in terms of t bar and r bar. If in terms of actually t star is similar, I just write this one. From here you can read, you can see, okay, the tt bar term finite, right? And then you got 2m actually equals 0. This guy is 2m equal minus 1, right? Because it's 2 times GTR. This is finite. Of course, this is finite. But you can also find t bar equal 1 plus 2mr. This is actually in my notes. You can find r equal minus 2mr. GRR equal minus 1 minus 2 mr. Our note is right. Okay, that's right. R squared and G phi equal minus R squared sin squared theta. You can see even in reverse, everything is finite, right? 1 R equal 2m. I do not have signal arc. My question is the following. Now this picture makes sense. All this is correct. Can you see where there's some problem with this picture? The problem is the following. GPR term, right? So if I consider let's say if I consider A equals delta A T bar. This is the vector along T bar direction, right? Tangential. I also consider RA equals delta AR. This is actually vector direction along R direction, right? This is actually my RA, this is actually say A RB G B equal G T bar R equal minus 2 and R. Not equal 0 unless R go to infinity, right? If it's not 0, what's the mean? They're not orthogonal, right? What about this picture? Are these orthogonal? It's not very correct, right? So this actually, you can see lots of textbooks, they say orthogonal. No, it's not orthogonal. That still makes sense. Okay, you can say, okay, I can cheat some people who actually just get each other. If you consider actually really, it's not correct. Why? Because you draw the picture axis T bar axis orthogonal to R, you are misleading in terms of size. You are drawing the angles of this angle depend on these properties. If let's say this x go like this, you still get the picture. The answer is okay, you get it roughly the same, not problem. But regularly speaking, this is incorrect. The same thing for T bar R. Okay? So that's actually, whenever do something, do not trust so much. Better if you want to work with it. I'm beginning to consider a solution. You need to first check if the solution is very solution. Sometimes you spend lots of time, you finally find, oh, that's actually a solution. The paper was wrong. If the paper was wrong, all the things that you need to work on, based on that, was also wrong, right? You just wasted time. Okay? So this is actually what I want to see here. Any question on this part? So now, like what I said, here actually is the white hole, another picture is black hole. We want to see what's happening with this actually two different pieces. Okay, I'm going to erase actually. Let's now we still have our we are until 11 o'clock. We still have half an hour. I want to go to the next lecture because the next lecture we cannot finish within 1 hour and a half. We need more time. So then you want to see, even adding the fingers to the code is cause confused. The really final resolution for this acre confusing comes from Korska-Zachman experiment. Yeah? So I would like to start from the general case, yesterday Professor Sushant consider, remember the starter case FR dt squared minus HR d r squared minus r squared d squared omega. So this is the most general rigorous measure starter case. If it's a time depending, you just put a r as RT, then we use like a E2 nu T R and E2 lambda T R. So when the starter case, you just drop the time dependence is the same. We just use different notation, right? So from here you can see I'm going to, this is where I will take F out. This will give me dt squared minus h r f r d r squared minus r squared d squared omega. The reason I do this is because I just introduce another new radial coordinates. So I will set dr star equal square root h r f r d r. So just because this actually ever since something so far, actually you print for you. So then you can see in terms of this, I will need this equation. I have a ds squared equal fr dt squared minus dr star squared minus r squared d omega squared, right? The reason why I do this is because from here, you can see I can, let me see if I introduce this accuracy equations 2v dv equal dt plus or minus dr star. Over here I can write the dt equal dv minus or plus dr star. So then I have ds squared equal fr dt squared gives me dv squared minus 2 plus, sorry. This should be minus plus 2 times dv dr star. This angle minus plus dr star squared, then minus dr star, right? And minus dr star squared minus r squared d squared omega. This will give me f dv squared plus minus 2 f dv. Now I put dr star back, give my dr squared. This will give me h r f r d r minus r squared d omega squared. This f r dv squared minus plus 2 h f. So I simply, okay, let's write again. dv dr minus r squared d omega squared. This will equal fr dv squared plus minus 2, I simply call br dv dr minus r squared. This is the most general adding the fingers to the curve. You see, it's worse than. So this actually, well, I can write this physical equations are true. This is 4. So this we call Schwarzschild-like corners. This is like adding a Finkelstein corner. So this is for the most general case, right? So now, of course, we know for the vacuum case, we have like H R equal 1 over F R, then you get like B R equal 1 and R star equal square root F squared R1 dr. I can simply write this following. This actually will be R minus 2 and dr. Right? So you see here, I should have actually plus. Obviously, what is why? Because it's always positive. Right? So then you can say actually, I can easily integrate this one. This will give me R plus 2 log R minus 2. Or I did simply R star. So this actually this is called the adding the finger currents. Then you can see I have two orbital functions, right? F and B. Instead of you can use B to define like F and H. So here I have two orbital functions the same. So this is called normally Schwarzschild-like coordinates. I use the Finkelstein coordinates. So in that coordinates you can see now, if for the Schwarzschild solution I have G, let's see here, G V equal F, right? And G V R. Here B equal 1 because F equal inverse F. So this actually means G V either equal plus 1 equal minus 1. And G R equal 0. G theta equal minus R squared. G phi equal minus R squared. 6 squared theta. Right? So I can also find the inverse. Inverse, you can easily find this on. This is actually none. This GV equals 0 and GVR equal plus minus 1 and GRR minus FR. And G theta equal minus 1 over R squared. G phi equal minus R squared. So this is a Schwarzschild solution where of course F R equal 1 minus 2 and R, right? Then you can see now the is singular, correct? So which means actually in the Finkelstein, in the adding the Finkelstein coordinates, the metric is no longer singular and R equal to N. So we're actually successful connect the inside of black hole and outside of black hole, right? So there's actually, you see I have a minus sign, plus sign actually. The minus sign normally we call the ones time. So this actually, in this case actually the V. For the minus sign, the V actually coordinates represent at once. For the minus sign, we call time. So not a real time, it's actually no vector. like t plus r and t minus r. So one diagram you can see this represents in one case called ingoing, another case is outgoing. We'll come to this point. But what I want to see here, this is actually the most general static spherical symmetrical metric. Then you can write this in terms of Schwarzschild-like coordinates or anything fingers coordinates. This is a general case. You can actually, like Professor Sushant showed us, yes, they use maple to find different solutions. You can plug into equation. This measure could be for any series, right? Your incident theory, vacuum case equal fixed. What about non-vacuum case, right? Well, what about when you modify series? Then the equation will not be instant. So you will get a different V. You can work in this, you can work in this. Or sometimes you will find you will work in astrometric coordinates like yesterday we work out rho instead of r. T rho actually even better. You can find the exact solution. This is very depend on the equation and the program series. Which coordinate is better? We do not know. You have to try all, right? But you just aware of this. There are different coordinate choices. Okay. Here actually you will find in this case actually the identification coordinates are good. Okay. Any question about this part? So this actually I introduced this R star. You will find R star very important. Now yesterday I think when we talk about the motions, I think you come back to consider this arrow. This will give us, for example, G, A, B, X dot A, X dot B. This is actually the Lagrange. You can actually get a motion. So depend on this can be equal 1. This time like 0 is null, or like -1 is spacelike. The geodesics are just things. So for the over right here. Therefore, actually, if we consider this case now, ds squared equal f r. No, let's see. If I consider this actually in the spherical coordinate, this will be f r t dot squared minus r dot star squared minus r squared d. And theta dot squared plus sin squared theta dot squared. This is actually the extent we just brought here, right? You can see here. So I'm interested in this. Now, dot is dt. This actually, let's say, along this is the fine parameters along the trajectories. So if it's a time like I can use U as my proper time, the no vectors, this cannot be proper time. So this is the same thing, R stars, d R stars, du, and theta dc, u, same thing, theta, phi, du. Okay? So now if I consider the radial geodesic, what means radial geodesic? We have actually this one, z, x, y. So this actually theta, this phi, right? Angle theta. So radial geodesic means I have fixed theta, fixed phi, right? So for the radial geodesic, this can be yin going. can be outgoing, but along radial directions. So theta equals theta constant, phi equal phi 0. Then all we have is theta dot equal phi dot equal 0, right? So then you can see now my error becomes f r t dot squares minus r dot star squares, right? This egg. So for the non-geodesic, we just say, okay, it's 0. So I get simple 0, right? Then I even do not need to solve actually the order Lagrange equation. I just simply use this factor L equals 0. You see, now L equals 0 actually leads to T dot equal plus minus R star. Right? All I have actually dt du equal plus minus dr star du. Then I have actually dt equal plus minus dr star. So I just integrate this both sides. This actually will give me plus minus, you already know. This actually r star, right? All I have t equal plus minus, let's see. I'm going to put one constant. For r star plus one constant is equal plus minus r plus 2 and plus. So should it be, do you remember what's the equation should be? 7? Let's call this equation 7, sorry. So this actually our geodesics. This actually in my notes you can find, actually I skip this part directly down here, right? So now we want to understand what's happening, okay? So you can see now we have actually, let's see how I define here. So we reduce the t bar equal t plus 2 n log r minus 2n and t star equal t minus 2n log r minus 2n. This is actually our, what I just introduced, okay? Then you find this actually, this is the geodesics, right? When the plus sign is ingoing, minus sign is outgoing, or vice versa, we will see there. It depends on where it is. So if we write t stars equal this one, then you can see t bar equal t plus 2 and log r minus 2 and so this actually t equal minus plus, so this actually equal 2 and log r minus 2 and this actually I'm going to substitute my t here, right? So this actually t because I want to see in terms of my T-bar how all the ingoing geodesic comes. This is a geodesic equation, the light. So if I do something like this, they give me a plus minus R plus 2m log R minus 2m plus C0, right? So this actually, if I consider this, let's say, consider plus sign. If a plus sign is R plus 4m log R minus 2 m plus C0, right? This is actually for the plus sign. Now for the minus sign, this actually, this guy's cancel with this one. I have only minus R plus C0. So this actually for the minus sign. Or I get T bar. This is actually my equation is 9. Yeah. What I'm going to do actually is, now I want to see what's happening in the T bar and the R plane. What's the curve, the length of the ingoing outgoing. So this is my purpose. So I want to please follow me. So we just get this is the light traveling in this ingoing, outgoing, the light or no geodesic traveling. This is on the trajectory, right? You saw T equals this one. So I will actually draw this line in the T bar and the R plane. I want to understand how light actually, the trajectory of light in the regions inside, outside the black hole. So this is actually my purpose. Any question about this part? Okay. Now, let's see. You can always get it reversed. Just tell W equal VW, right? It's symmetric. So this actually gives us from here you can see we have normal singularity, right? So of course this GWW tail equals 0. So only no diagonal term. Diagonal term in the tail plane, in the V tail W tail plane equals 0. So this actually I do have diagonal term. So here you can see clearly for R equal to M equal minus 1, everything is fine, right? So then the extension is done. Now the problem is, how do you know this is maximum extension? Right? Remember when we draw when we use adding the Finkelstein coordinates, if we use the VR, then we get a white hole for the advance time. Then for the retire time, we'll get a black hole. So all is unified region 1, region 2, right? So here you will see this actually we have not only unified region 1 and region 2, we have actually region 1 prime, 2 prime. We have 2 extended regions. Because of these 2 extended regions, you can see the space-time is called geodesically complex. What means geodesic complex? This is actually, for example, now let's consider we're actually time-like test particles in this actual universe. So we can move either from minus infinity to t infinity. So this is our trajectory. Or when do we actually from minus infinity hit the singularity? This is called geodesical complex space. So space-time has singularity. But you either from minus t infinity to hit the r equals 0 term, or just simply from t equal minus infinity to t plus infinity, let's say I'm moving from one standard r to another r. So that's fine. So this is called geodesical complex. And let's say you know, if I do not hit singularity, I know what's the next step I'm doing, right? So this is called actually geodesically complex space. You will find in terms of this guys, I have 4 regions. 2 represent actually corresponding to the Sushant plan, region 1, region 2. I have 2 external regions. If I consider all of them together, I get a geodesically complex space-time. That's perfect. And more important, like what I emphasized before, this extensive from R less than 2m to greater than 2m, cross this R equal to m, the extension is analytic. Remember the importance, why analytic? If it's not analytic, you can have infinity extension, right? Like what I said, very simple example, I have actually see, this is my x, if I have x equal x for x greater than 0. So how do I extend this to x negative? I can do something like this, right? Reflection. This is just to give me x. But you know this is not actually continuous. There's actually the derivative on this point actually discontinuous, right? I can do something like this. You can do whatever you want, as long as this actually can be continuous, if you want to. Even though this continuous derivative, for example, I have step function, that's fine. This is also one extension. It's not continuous, there's a jump. That's fine, because mathematically makes sense. But my extension is unique. The unique requires, this is the only one. Right? So that's why I say, okay. Critical extension is unique and geodesically complex. This is mathematically perfect, right? So this is the only one you get a unique extension. This is the only one you get the maximum space-time. So the rest is us to understand what's the physics. So we have been understanding this for more than 100 years. I still try to understand this. We have, you heard, prior world, membranes, all the ideas, try to propose what's happening near the horizon. Try to see if the information is lost or not. Why this is so important? Information, if it's lost, then it's connected with no unit term. No unit term means GR is not a quantum. Then you have all the problems come out, right? So that's why it's so important to the black hole information loss. Last year, 2 breakthrough work, did one by group from Princeton. So another one actually did from Harvard by University. So this year he finished his PhD, he got a immediate offer in Berkeley for assistant professor, which is normally almost never happen in the US. In order to get a faculty position, you need a postdoc. So he got an assistant professor because it's Berkeley. Okay? So we have 4 main papers. I will stop it here, and next time we'll continue this. I think we have enough time to finish next.
Okay.
So, any questions? Yeah.
No, that's right.
That's fine? Okay, let's go here.
So, to couple of announcements. So, we will have photograph at lunch. Right, one here and one down. Because that is important. And we will also give you copy of food. And there are some people who will be coming, right? So that afternoon there is one tutorial, one lecture. Now idea is that this is course will go on, but we have to talk about what is happening in the research. So it will not be the blackboard talk. It will be giving overview of gravitational lens. Okay. It's a general talk. Detailed calculation will take 3-4 days, right? So it will be general talk. Any difficulty in calculation, you can ask me later. So I'll give a flavor of gravitational lensing in the afternoon. And Misbah will help us with, she will give you how to, yesterday I said that mathematics is useful in plots and numerical calculation. So she will demonstrate some capabilities of mathematics today. Right, so one tutorial, one talk. Right, so don't go away anywhere. Before lunch you will have photograph.